Hello everyone, my name is Sohail Akhtar Qureshi and today I am going to give you a presentation on the topic raycasting. In computer graphics, raycasting is the most basic form of ray tracing. Raycasting is a fundamental technique in computer graphics. It involves simulating the path of light rays as they interact with the objects in a virtual scene, allowing for realistic lighting and shadowing effects. Now let's understand what raycasting actually is. I- In raycasting, it allows objects and surfaces to be detected and their properties, such as color and lighting, to be calculated. Raycasting is the basis for many rendering algorithms, including ray tracing and rasterization. In the earlier days, raycasting was used in video games as it was of low quality, but it was faster working. Now, the working works on the main principle behind raycasting is that the rays can be cast and traced in groups based on certain geometric constraints. In raycasting, a ray from the pixel through the camera is obtained and the intersection of all objects in the picture is computed. Next, the pixel value from the closest intersection is obtained and is further set as the base for the projection. Here we can see in the picture that raycasting is distinct from ray tracing, with raycasting being a rendering algorithm which would never recursively trace secondary rays, while ray tracing is capable of doing so. Now, what are the applications of raycasting? First, 3D rendering. Raycasting is a fundamental technique used in real-time 3D rendering engines to generate realistic images by simulating the behavior of light rays. Computer vision. Raycasting is employed in computer vision algorithms to detect and recognize objects by analyzing the intersections of simulated light rays with the environment. Medical imaging technologies in medical imaging technologies such as CT scans and MRIs, and to reconstruct 3D models of the human body from 2D slice data. And the most important is the video games, as I mentioned earlier, that it was of low quality, but due to its fastness, it was used in the earlier video games also. What are the advantages of raycasting? Raycasting is a powerful technique that offers several key advantages. It provides accurate and realistic rendering, allowing for detailed simulations of light interactions. The algorithm is relatively simple to implement, making it an efficient and cost-effective solution for many applications. Additionally, it enables seamless handling of complex geometric shapes and materials, providing a versatile approach to visual representation. The technique's flexibility and efficiency make it a go-to choice for a wide range of industries, from gaming and film to scientific visualization and product design. With advantages, there comes disadvantages. Here in raycasting also, there are some disadvantages which are compared to ray tracing, the images generated with raycasting are not very realistic. Due to the geometric constraints involved in the process, not all shapes can be rendered by the raycasting. Restriction imposed by current GPU architectures, which may limit the performance and capabilities of raycast interaction. Implementing raycasting in 2D. Raycasting in 2D involves shooting rays from the viewer's position and detecting collisions with objects in the scene. This allows efficient rendering of simple 2D environments such as top-down or side-scrolling games. The algorithm works by iterating through a grid of pixels, casting a ray from the viewer's position to pixel in with intersection or with objects in the scene. Implementing raycasting in 3D. In 3D, raycasting is implemented through 3D geometry representation. Raycasting in 3D environments requires the accurate representation of complex 3D objects and surfaces. This involves using advanced modeling techniques to capture the intricate shapes and details of the virtual world. Ray object intersection is detecting the intersections between the cast rays and 3D objects in the scene. Efficient algorithms are needed to quickly compute these intersections for real-time rendering. Handling occlusion in 3D environments, rays can be occluded by intervening objects, requiring advanced techniques to accurately determine which surfaces are visible and which are hidden from view. Camera and perspective. Properly configuring the virtual camera and its perspective is crucial for realistic 3D ray casting, ensuring the rays are cast from the correct vantage point and direction. What are the algorithms in ray casting? Ray tracing. Ray tracing is a popular ray casting algorithm that simulates the path of light rays to determine pixel color. It accurately models reflections, refractions, and shadows, but can be computationally intensive. Digital Differential Analyzer, also called as DDA. The DDA algorithm uses linear interpolation to efficiently trace rays through a 2D grid, making it a fast and simple raycasting technique often used in 2D games and graphics. Bressenheim's line algorithm. Bressenheim's algorithm is an efficient integer-based approach to drawing lines that can also be adapted for raycasting in 2D spaces. It avoids costly floating point calculations. Raycasting optimization techniques. There are several ways to optimize raycasting, so- which are spatial partitioning, bounding volume hierarchies, coherence-based optimizations, parallel processing. Spatial partitioning. Techniques like quadratic trees and octares divide the scene into smaller, more manageable regions, reducing the number of objects that need to be tested for intersection with each ray. Bounding volume hierarchies. Constructing a tree-like hierarchy of bounding volumes around objects allows for efficient ray-object intersection, skipping entire subtrees if the ray misses the bounding volume. Coherence-based optimization, exploiting the fact that nearby rays often intersect the same object. Ray tracing algorithms can use reuse computation and avoid redundant work. Parallel processing, distributing the workload of raycasting across multiple CPU cores or GPUs can significantly speed up the rendering process, especially for complex scenes. What are the challenges in raycasting? There are various challenges in raycasting such as precision and accuracy, performance constraints, occlusion and transparency, aliasing and sampling. What are the future developments in raycasting? In the near future, we can see the developments in raycasting such as improved algorithms, hardware acceleration, virtual reality integration, machine learning advancements. At last, the conclusion. In summary, raycasting stands as a fundamental technique in computer graphics, pivotal for determining visibility and intersections within virtual environments. Its efficiency, flexibility, and ability to produce accurate results make it indispensable for rendering scenes with various geometries. Despite its advantages, raycasting has limitations, particularly in handling advanced lighting effects and complex scenes, while also being susceptible to aliasing artifacts. Nonetheless, when used in conjunction with other rendering techniques, raycasting contributes significantly to the creation of visually appealing and realistic computer-generated imagery. I hope at last, I hope that I am able to explain you raycasting in easiest and simple manner within a short period of time. Thank you everyone for watching this video. Thank you.